So welcome to the 2006 AP Calculus video, where I'm going to be going over the released exam from this year. So the first question, we have R being the shaded region, bounded by the graphs of y equals ln x, and the line y equals x minus 2 as shown here. Part A, find the area of R. How creative. Okay, so what we want to do is when we're trying to find the area of a region, the first step that we want to take is to find the x-coordinates of these intersection points, where the two relevant curves are touching each other. Don't go there. So there's these 2 points here where they're touching each other. Don't. And we want to find their x-coordinates. So the way we do that is by setting these two equations equal to each other, because this is the point where they intersect. So we'll take ln x, and then x minus 2, and by setting them equal to each other, we'll get the x-coordinates where the two curves meet. So when you do this, you'll get two answers, because there are 2 points. You'll get x equals 0.159, and you'll get x equals 3.146. And the way you do that, if you don't know already, is by putting it in a graphing calculator. This is the fastest way in my opinion, putting it in the graphing calculator and finding the intersection point between these two. Okay, so you do this, you get these two values, and for the sake of accuracy, I'm going to store these values in my calculator. So I'll store this one as A, and then I'll store this one as B, and I'll label that here as well. This is x equals A, and this is x equals B. So now for the rest of the parts of the problem and this part, whenever I'm referencing x equals A and x equals B, I'm referencing these points, the intersection points. So now if I want to find the intersection point, so next step is we want to find the area, right? The way we do that is by using the idea that this curve here is on top and this curve here is on bottom. The top curve is the natural log of x, the bottom curve is x minus 2. So we have a formula where we're integrating, I'm doing white, we're integrating, and it's the top curve minus the bottom curve. So the top curve is ln x minus the bottom curve is x minus 2. And then the bounds of the integral are where we're starting, which is x equals A, and then where we're ending, x equals B. So if you take this and put it in your calculator, you will get 1.949. Okay, so for points, 1 point for the correct limits, 1 point for the correct integrand, 1 point for the correct answer. So part B, we need to find the volume of the solid generated when R is revolved around the horizontal line y equals -3. Let me sketch that line here real quick. So something like that. And by the way, if you want to verify that the line is indeed under the point x equals A, the simplest way to do that is by taking x equals A, plugging it into either of these equations, and realizing that the y-coordinate is in between 0 and -3, so it is correctly placed here. Y equals -3 is below it. So the next step now is to what I like to call identify the expressions for the two radii. And by the two radii, I mean one radii is going from the line that we're rotating around to the first curve. I'm going to draw that, let's draw here, yeah. The line that we're rotating around to the first curve, and then the line that we're rotating around to the second curve. I have two different radii like that. So now we need to find equations for these two radii, or expressions. Okay? So the first one is going to be going, this first radius here, it's going to be going from -3 to 0, so that length is 3, and then it's going from 0 to x minus 2, right? Because this extra distance here, it's the y-coordinate, it's the height, sort of, and that height is x minus 2. So we're going 3, and we're going x minus 2. So I can say that little r, we'll call it little r, lowercase r, equals 3 plus x minus 2, or x plus 1. Okay, and now for uppercase r, or big R, it's a similar idea. It's going from -3 to 0, so this distance is 3. And then we're going from 0 to the upper curve, from 0 to ln x. So this height is ln x, and we're doing ln x and 3. So our big R is 3 plus ln x, like that. Okay, so now that we've done the hard work for ourselves and identified the two radii, okay. So we'll just use our formula now, which is pi times the integral from a to b, again a to b because a is our starting point, b is our ending point, of big R squared minus little r squared dx. I'm going to save you the time of watching me just rewrite these equations, or rewrite these expressions in the integral, but basically you take this, put it in here, square it, take this, put it in here, square it, integrate from a to b, multiply by pi, and you get your answer. So if you do this, you will get 34.199. So for points, this was a 3-point question. 1 point for the answer and the integral, or sorry, 1 point for the answer and the limits and the constants. All three of those combined is 1 point, and then the integrand is 2 points. Part C, write but do not evaluate an integral expression that can be used to find the volume of the solid generated when R is rotated about the y-axis. So now we're rotating about the y-axis, so now we're dealing with kind of tilt our head sideways, if you will. So again, we still have two radii, just like we did before. The first radii is going from the thing that we're rotating around to the first curve. Now notice this time the natural log is on the bottom. And then the upper curve, or the big radius, will be like that. Okay, this is big R, and then this is little r. Okay, and now since we've tilted our our whole framework sideways, we want to take our two equations, y equals ln x, y equals x minus 2, and we want to rewrite them so that it's instead of y equals something, it's x equals something. Okay, so instead of y equals ln x, we'll solve this for x by making these both exponents with the base of e. So that allows us to cancel out the e in the natural log. So we get that x is e to the y. And then for y equals x minus 2, we'll add 2 to both sides to get us x is equal to y plus 2. So now these are the, since now these are kind of the heights, if you will, for the radius, these are going to be what we're using in our expression. Okay, so for the little radius, little r, it's just going to be the height from the y-axis to the bottom curve, right? So we're starting at x equals 0, and we're going to x equals e to the y, because that's this. So it's starting at 0, going to e to the y, that total distance is e to the y. And then for our big radius, we're starting at 0, we're going to y plus 2. So since we're going from x equals 0 to x equals y plus 2, that is a distance of y plus 2. So just like before, we're going to do the equation that we know. It's going to be pi times the integral from the starting point to the ending point. Okay, here's where it gets different. So the starting point and the ending point. We still have the same starting points and ending points. These are the starting points and ending points, but we're not dealing with the x coordinates anymore, right? We're dealing with the y coordinates. So I'll write it again. This is x equals a, this is x equals b, but we're doing everything in terms of y now, right? Since we're solving everything in terms of y, since we're rotating on the y-axis. So I don't care about the x intersection points, I care about the y intersection points. And the way I'm going to do that is since this is on the curve y equals ln x, I can say that the y coordinate, I'll do it under here. So I can say the y coordinate is the natural log of x, the natural log of a. Then similarly, I can say that y is the natural log of b. Alright, so with that in mind, I can make sure that these are my actual limits of the integral, the natural log of a or the natural log of b. There were other ways you could have done it. You could have used this equation here to get your limits for the integral. You could have actually solved for them by setting the y's equal to each other. It's a matter of preference. I think it's easiest. So we have this, and then it's still going to be big R squared minus little r squared. So we'll have big R, which is y plus 2 squared minus little r squared, which is e to the y squared. And instead of dx, it's going to be a dy, since everything is in terms of y. Okay, so they didn't want us to solve for it, they just wanted us to write the expression. So that's going to be our final answer. This was a 3-point question, 1 point for the constant pi and for the correct limits. The other 2 points are for the correct integrand. That was the end of question 1. Moving on to the next question. Alright, in question 2, we're dealing with an intersection at Thomasville, Oregon, where cars are turning left at the rate L of t is 60 square root of t times sine squared of t over 3 cars per hour over the interval from 0 is less than or equal to t is less than or equal to 18 hours. The graph of y equals L of t is shown below. I had to move it there because of space reasons. Yeah, okay, and moving on. So, part A, to the nearest whole number, find the total number of cars turning left at the intersection over the time interval from 0 to 18. So to do this, we're going to look at L of t a bit more closely. So what exactly is L of t showing us? It's showing us at any particular time how many cars per hour are traveling through the intersection, right? So like at time t equals 2, I can know exactly how many cars per hour are traveling through the intersection. But I don't want the number of cars per hour at a certain time. I want to know the total number of cars over a long period of time, right? So the way we do that, since we're going to be adding up all the individual cars per hour for t equals 0, t equals 0.1, 0.2, and the infinite number of t values from 0 to 18, that adding up an infinite number of stuff should symbol integration, should make you think of integration. So to find the total number of cars turning left, we'll be integrating L of t, and the time for that is from 0 to 18, right? And this time I'll actually write it out. So we'll be integrating from 0 to 18 of 60 square root of t sine squared t over 3 dt, and this should give us the total number of cars over a long period of time. And the units check out as well, because cars per hour multiplied by hours give us cars. So this, if you put this in your calculator, you will get 1658 cars. Like so. This was a 2-point question, 1 point for the integral, 1 point for the answer. Traffic engineers will consider turn restrictions when L of t is greater than or equal to 150 cars per hour. Find all values of t for which this occurs, and compute the average value of L over this time interval. Indicate units of measure. Okay, so looking at the graph of L of t that we have here, we want to find when it's greater than 150, right? So 150, if I draw like a line there, I'll do it in black, yeah, sure. That's this right here. We see that it's starting here. It goes above 150 for the entire time interval, and then it ends here, right? So we need to find these 2 points. The way we do that is we'll take L of t, which is, again, 60 square root of t sine squared t over 3 yada yada, right? And we'll set this equal to 150. That'll give us these 2 t values. So if we were to do this in our calculator, we would get that t is 12.428 and t is 16.122. And just like we did in question 1, we're going to set this equal to a, and I'm going to set this equal to b, and I will label it as well for your convenience. T equals a, t equals b. So I can erase this. Okay, so we know that we want to figure out all values of t for which L of t is greater than or equal to 150. So we'll say L, wrong color, L of t is greater than 150 for A is less than T is less than B, but we want to know when it's greater than or equal to 150, so we'll just put a couple of equal signs there, and that was that. We also need to find the average value of L over this time interval, right, from A to B. So the equation for the average value of a function on a time interval is 1 over B minus A, we'll get to that in a second, times the integral from A to B of L of t dt. And I'll explain all of this in a moment. So the A and B part, we're starting at A equals B. We're starting at T equals A. We're ending at T equals B. So that's how we got the B minus A part. This is ending minus starting, and the integral from starting to ending. Then L of t is the function that we're interested in, dt. Okay, so this is the average value. Remember, B and A are actual numbers that are stored in our calculator. And L of t is a function that we know. So we can take this whole thing and compute the average value to get to be 199.426. And we need units for this, right? So since we're dealing with the average value for L of t, that's the average value is a value of L of t. So the units for the average value of L of t is the same as the units for L of t. L of t has units of, they told us here, cars per hour. So this also has units of cars per hour. Like that. Awesome. So in terms of points, 1.4 correctly stating that L of t is greater than 150 for this A and B there. 1 point for the correct integral for the average value. 1 point for the correct answer for the average value. Okay, part C. This is kind of a weird one. Traffic engineers will install a signal if there is any 2-hour time interval during which the product of the total number of cars turning left and the total number of oncoming cars traveling straight through the intersection is greater than 200,000. In every 2-hour time interval, 500 oncoming cars travel straight through the intersection. Does this intersection require a travel signal? Why or why not? This is actually a very, very simple question, but they're making it kind of confusing. I'm not sure why it's a very weird question. So anyways, we're not going to worry about that. We're just going to solve it. So we want to say, okay, so if we take the number of cars turning left, so cars left, and the total number of cars traveling right, or sorry, cars traveling straight. So we want to take this, we want to take the product of them, so we'll multiply them like that. So we want to say, okay, is there any time where this is greater than 200,000? Okay, if there's any time where this is greater than 200,000, any 2-hour interval where this is greater than 200,000, then the answer is yes, we do need a traffic signal. And they're also giving us that 500 cars are traveling straight through the intersection. So this cars straight is 500. So we'll say that cars left times 500 has to be greater than 200,000. Then cancel those, 5 divided by 2,000 is 400. So cars that are turning left has to be greater than 400. Okay, so basically now we're asking, is there any 2-hour interval where the number of cars that are turning left is greater than 400? And from our graph, it seems like there's a pretty clear time where that's happening. Just look at this. So if I again draw my horizontal line y equals 200 like that, I see that from t equals 13 to t equals 15, like that-ish, we see that those are both, I think they're both above 200. This one's very close to 200. So if you add these together, you're probably going to get something that's over 400. Okay, so what we'll do now is we'll say, okay, this is clearly over 400. We just need to prove it mathematically, right? So we take this number and we're to add that up, we'd get something that's over 400. So the way we're going to do that is we're going to integrate from 13 to 15 our L of t function to give us the total number of cars at a certain time dt. And if we do this, we'll get 431.931, which is clearly greater than 400. So the answer is yes, we are going to need a traffic signal because from 13 to 14, the total number of cars entering is greater than 400. Yeah? Sounds awesome. So, in terms of points, this was a 4-point question. 1 point for correctly determining that the cars turning left had to be greater than 400. 1 point for the limits of the integral. 1 point for the answer of the integral. 1 point for the correct assertion that we do need a traffic signal. That was into question 2. Moving on to the third question. So for question 3, we have the graph of the function f consisting of 6 line segments. Let g be the function given by the integral from 0 to x of f of t dt. In part A, we need to find g of 4, g prime of 4, and g double prime of 4. So let's start with finding g of 4. So to find g of 4, we'll simply plug in 4 into x. So that'll be the integral from 0 to 4 of f of t dt. Right, so that's the area from 0 to 4. So we're starting at 0 and we're going to 4. So that'll be this area, this area, this area, and this area. Right, so this triangle and then this this quadrilateral. So notice right away that this region here and this triangular region here, they'll cancel out. This is negative, this is positive. So we can just focus on this remaining piece. So we'll have this rectangle, which has an area of 1 times 2 is 2. And then we'll also have this triangle, which has an area of half of the rectangle. So it'll have an area of 1. So these both combine to equal 3. And then again, we don't need to worry about those because those canceled out. So g of 4 is 3. Okay, next, for g prime of 4, first let's just look at g prime of x and notice that it's the derivative with respect to x of this, the integral from 0 to x of f of t dt. And now according to the fundamental theorem of calculus, this is equal to f of x. This whole thing here is equal to f of x by the fundamental theorem of calculus. So this is something that you want to know because they'll ask you this a lot, so you might want to know that. And we just conclude, so we're going to say now that g prime of x equals f of x. So g prime of 4 therefore is f of 4. And looking on our graph of f of 4 is 0. Finally, we're asked g double prime of 4. Well, since g prime of x is f of x, we can go one step further and see g double prime of x is f prime of x. So g double prime of 4 is f prime of 4. That's the slope of the line at x equals 4. So that's the slope of this line segment here. And since when we go over 1 in x, we go down 2 in y, the slope is negative 2. If you want, you can use these points and, actually find the slope, but that'll take too long. So we found g of 4, g prime of 4, g double prime of 4, 1 point, 1 point, 1 point. In part B, we need to find if g has a relative minimum, maximum, or neither at x equals 1. So since we want to figure out stuff about g, and all the information we have in the form of this function is about f, we need to figure out a way to relate g and f, right? So if g has a relative maximum or minimum, what does that tell us about f? So we'll say, okay, so if g has a relative extrema, right? Relative extrema being either a minimum or a maximum, then we can say that the definition of a relative extrema, that's where its derivative switches signs, right? So g prime switches signs from negative to positive or positive to negative. And then since g prime of x is the same as f, like we determined earlier on, we can say if g prime of x switches sign, that's the same as saying f switches sign. Okay, so f switches sign. So if g has a relative extrema at x equals 1, then f will switch sign at x equals 1. And if we look at the graph of f at x equals 1, we see originally f is negative, and then at 1 it switches, and now it becomes positive after 1. So we do have a switch in sign at x equals 1, so we do have a relative extrema. But to figure out whether it's a minimum or maximum, we can say, okay, if it was a minimum, where the function has a negative derivative originally, and then it'll switch to a positive derivative, it'll be something like this. And then on the other end, if it starts with a positive derivative, and then it switches to a negative derivative, we have a relative maximum like so. This is a minimum, and this is a maximum. Since we originally have a negative derivative, and then we go to a positive, going from negative to positive, here we have a relative minimum. So we can say, alright, g has a relative minimum at x equals 1 because g prime of x switches from negative to positive. And that's just a little thing you might want to do when they're asking you about g. Talk about g in your explanation instead of f. I don't think you have to, but that's just what my teacher taught me, and that's what I tell you to do as well. So this was 2 points. 1 point for correctly saying that there's a relative minimum at x equals 1, and then another point for an explanation. Part C. Suppose that f is defined for all real numbers x and is periodic with a period of length 5. The graph above shows 2 periods of f. So by periodic, they just mean that it repeats over and over and over again, kind of like a sine curve. So we're given that g of 5 equals 2. We need to find g of 10 and write an equation for the line tangent to the graph of g at x equals 108. Whoa, okay. So let's see what we can do. We know that g of 5 is 2, and the first thing they want us to do is they want us to find g of 10, right? So g of 10 is the integral from 0 to 10 of f of t dt. And then now notice that we can, since f just repeats on and on forever, we can just split it up into one sort of period, right? So we can split it up into, this is one of its periods, and then this formation just repeats over and over and over again. So in this one period, the net area here would be this, this, and this, right? But also this will cancel with this, and then this will cancel with this. So the net area is the same as this, which is 1 times 2 is 2. So for every period, the net area is 2. So g of 5 is 2. G of 10 will be one more period, right? It'll I can't use black. It'll be, let's do blue. Yeah, it'll be one more period across, right? So if at g of 5 the total area is 2, if we go another 5 over, so we go another full period, then the area is going to be another plus 2, right? Because every time we do a period, we're gaining 2 in area. So g of 10, therefore, is going to be g of 5 plus 2. We don't actually even need this, do we? G of 10 is g of 5 plus 2. G of 5 is 2, so 2 plus 2 is 4. Right, g of 10 is g of 5 plus one more period, which has an area 2. Okay, so that's g of 10. Now they also want us to write an equation for the line tangent to the graph at x equals 108. Oh boy. So 108 is pretty obvious. They don't want us to do anything fancy here. They just want us to see, okay, what's the pattern going on? So like we said, every time x increases by 5, the area increases by 2, right? That's the pattern here. So we can say g of 100 so we can say g of 105, right? Since that's gonna be the end of one period, we can say g of 105 is, since each each period has an area of 2, we can say g of 105 is 2 times the number of periods up to 105, which is going to be 105 divided by 5, which is 26, I think? Is it 21? I don't know. 21, yeah. So if we do this, this comes out to be 42. So we want, since we're looking at 108, g of 108, that's going to be g of 105 plus the integral from 105 to 108 of f of t dt, right? So this is, we're starting at the beginning of a period, and then we're going up by 3 x values, right? Let me erase all this right now. So we're starting at the beginning of a period, and then we're going over 1, 2, 3. So if I just imagine this is at x equals 105, we're going 1, 2, 3. So this is the area that we're interested in, right? So the net area is going to be this, from 105 to 108. And like we said before, this is going to cancel with this. So the net area is just going to be this, which is 1 times 2 is 2. So since this integral is equal to 2, therefore g of 108 is 42 plus 2, or 44. Okay, so why do we want that? Well, since we're trying to find the line tangent to the graph of g, we want to figure out the point there and the slope there, right? So the point is 108 comma g of 108, right? Which is the same as 108 comma 44, right? Since g of 108 is 44, the next thing we need to write the equation of the tangent line is the slope of g at 108. So that's going to be g prime of 108, right? And then remember how g prime is the same as f? So this can be the same as f of 108, right? What is f of 108? Well, we have to go back to the fact that this is repeating over and over and over again, and we can say, alright, this is f of 0, this is f of 5, f of 10 is also going to be negative 2, so it's f of 15, and then every single multiple of 5, right? So here, if we just keep going over, we can just imagine this is 105, right? This is f of 105, so this is f of 106, f of 107, f of 108 is the same thing as f of 3, basically. So f of 108 is the same thing as f of 3, or sorry, f of 3, because it's a repeating thing. And f of 3 is 2, as we can see, the point 3 comma 2. So this is equal to 2. And then now that we have our point, we have our slope, we can use point slope form to figure out the tangent line. Where point slope form is, remember, y minus y1, so this y coordinate is equal to the slope, which is 2 times x minus x1, so this x coordinate, 108, like that. And that is the equation of the tangent line at x equals 108. Is that all they asked for? Yes, that is all they asked for. Okay, so for points, this one is 4 points. 1 point for correctly finding g of 10, 1 point for finding g of 108, 1 point for finding g prime of 108, which is the slope, and the 4th point for writing the correct equation. That was the end of question 3. Next one. So question 4, we have a rocket that has a positive velocity v of t being launched upward from an initial height of 0 feet at time t equals 0. The velocity of the rocket is recorded for several values of t, where t is between 0 and 80 seconds, as shown in this table above. Part A, find the average acceleration of rocket A over the time interval from 0 to 80, indicate units of measure. Okay, so in part A, since acceleration, if you remember from the particle motion unit, acceleration is the rate of change of velocity. So it is the rate at which the velocity is changing. Rate of change of the velocity. So when they want the average acceleration, that's the same thing as saying the rate of change. That's the same thing as saying the average rate of change of the velocity, right? This average acceleration is the same as the average rate of change of velocity. So we can use the average rate of change formula for velocity. So the average rate of change of velocity from an interval a to b is going to be the velocity at that point b minus the velocity at the point a over b minus a. And since we're going from t equals 0 to t equals 80, a is going to be 0, b is going to be 80. So we'll have v of 80 minus v of 0 over 80 minus 0, or 80. So v of 80 and v of 0 we can find in the table. V of 80 being 49, v of 0 being 5. So it's going to be 49 minus 5 over 80. And then for the units of this, we want the units for acceleration. And since we're doing velocity divided by time, it's going to be the units for velocity divided by the units for time, right? So the units for velocity are feet per second, and the units for time are seconds. So it's feet per second divided by seconds, or feet per second squared. Okay, so the units for the acceleration are feet per second squared, like that. Squeeze that in there. Okay. This was a 1-point question, just 1 point for the correct answer. Part B, using correct units, explain the meaning of this integral in terms of the rocket's flight, and then estimate it with a midpoint Riemann sum with 3 subintervals of equal length. We like the equal length, that's easy. So, the first part, explain the meaning of the integral from 10 to 70 of v of t dt. Okay, so let me just write down the particle motion kind of like hierarchy, if you will. So at the start we have position, at the middle we have velocity, at the end we have acceleration. So if we're taking derivatives, we go this way, right? And then if we're taking integrals, we go this way, right, dx. Okay, so if you want to take the derivative of position, you're going to get velocity. If you're going to take the integral of velocity, you're going to get position. So you should know this kind of chart, I guess, if you don't know already. So if they want us to evaluate the meaning of the integral of velocity from 10 to 70, we're integrating velocity. So we're going to get the change in position, which is, since we're integrating velocity and not speed, the integral of velocity is displacement. So the integral of velocity is displacement. So since we're going from 10 to 70, that's going to be the displacement from t equals 10 to t equals 70. Right, so integral of velocity is displacement, and we're going from 10 to 70, so displacement from 10 to 70. So your explanation would say the integral from 10 to 70 of v of t dt is the displacement from t equals 10 to t equals 70 seconds. Okay, the second part of part B, use a midpoint Riemann sum with 3 subintervals to approximate it. So the way we'll do that is we'll say, okay, we're going to have, we first need to figure out what the length of each subinterval is. So we're going from 10 to 70, right? And then we're doing it in 3 equal subintervals. So each subinterval is going to be 20 long, right? The first is going to go from 10 to 30, and then it's going to go from 30 to 50, and it's going to go from 50 to 70. These are the 3 subintervals that we're going to do. Okay? So, let's erase that. Okay, so each subinterval is going to be of length 20, right? So the way the formula we use for a Riemann sum with equal subintervals is, first we'll have the common length 20 times, and then here's what we're going to do. So we're going to have v of t0 plus t1 over 2 plus v of t1 plus t2 over 2 plus v of, I'll explain what the t's mean in a second. You just go with it for now, okay? So what these t's are, these are the times that are representative of each of the subintervals. So remember, we're starting at 10, and then we're going to 30, and then 50, and then 70, right? This is our time 0. This is where we're starting. This is the first subinterval. This is the end of the second subinterval. And this is the end of the third subinterval. So I can go ahead and substitute for these t0, t1s, and whatnot. I can erase the t's and put it in the actual numbers from what we have up here. So 10 plus 30, 30 plus 50, and 50 plus 70. Okay, so this is the equation for the midpoint Riemann sum. And then if we simplify this a bit further, we'll get v of 20 plus v of 40 plus v of 60. And then that's going to be, if we look at the table, v of 20, v of 40, v of 60, 22, 35, 44. So 22, 35, and 44. That's the answer for the Riemann sum. And I'll leave a little bit of space for units. Since we're measuring the displacement, remember that it started at this position that we'll measure in feet, and then ended at this position that we're measuring in feet. So the change in position would be measured in feet, right? So since we're dealing with displacement, the units for this are going to be feet. That was a 3-point question. 1 point for correctly saying that the integral of the velocity is displacement. You could have also said it as distance because they specified that the velocity is positive. So the displacement or distance from 10 to 70 seconds. The 2nd point for the setup of the Riemann sum. The 3rd point for the answer for the Riemann sum. So in part C, rocket B is launched upward with an acceleration of a of t is 3 over square root of t plus 1 feet per second per second. At time t equals 0 seconds, the initial height of the rocket is 0 feet, and the initial velocity is 2 feet per second. Which of the two rockets is traveling faster at time t equals 80 seconds? Explain your answer. So when they're asking which one is traveling faster, they're asking us which has a higher velocity, right? So they're asking which has the higher velocity. We know that the velocity of the first rocket, I'll call it rocket, they're calling it rocket A. So the velocity of the first rocket at 80 seconds is 49 feet per second, right? So we need to figure out whether the rocket B's velocity is greater or less than that. Okay, so we're given its acceleration, and we need to find its velocity. So looking at the table that we drew earlier, we should say, okay, we want to integrate acceleration. So we'll integrate 3 over square root of t plus 1 to get our velocity function. And then since the coefficient with the t is just 1, we can treat this just like a regular square root of t. So we'll say, okay, this is 3 times t plus 1 to the negative 1/2. And then again, the coefficient is 1, I'll just pretend like it's a t. I'll raise this by 1 and then multiply by the reciprocal. It's going to be, raise this by 1, I'll get 1/2. Multiply by the reciprocal of 1/2, multiply by 2. So we'll get 3 times 2 is 6 times t plus 1 to the 1/2 power. And I don't need the integral sign anymore. Okay, so that plus c, that's the velocity function, right? So the velocity is 6 times t plus 1 to the 1/2 plus c. We know that the initial velocity is 2 feet per second, so we can say, okay, at time t equals 0, the velocity is 2. So 2 is 6 times 0 plus 1 to the 1/2 plus c. 0 plus 1 is 1. Square root of 1 is 1. 1 times 6 is 6. So 2 equals 6 plus c. And then c equals negative 4. So the velocity function v is 6 times t plus 1 to the 1/2 minus 4, right? And we want to figure out what's the velocity at time t equals 80, so we can compare it to the other rocket. So the velocity of the rocket B at 80 seconds is 6 times 80 plus 1 to the 1/2 minus 4. I would leave it like this if they just asked us what the velocity was, but since they want us to compare it, we're going to want to simplify it a bit more. 80 plus 1 is 81. The square root of 81 is 9. So we'll have 8 times 9, or sorry, 6 times 9 minus 4. 6 times 9 is 54. 54 minus 4 is 50. Okay, the velocity of rocket B, 80 seconds, is 50. Oh, look at that, they made it really close. Of course they did. So it's pretty clear here that at 80 seconds, rocket B is traveling faster. Okay, so your answer would be, yeah, rocket B is traveling faster. The points here, there are 1, 2, 3, 4, 5 points. 1 point for correctly taking the integral of the acceleration, 1 point for including the plus c, 1 point for using the initial condition, 1 point for finding the velocity of rocket B at 80 seconds, and then 1 point for stating and explaining that the velocity of rocket B at 80 seconds is greater than the velocity of rocket A at 80 seconds. 1 point for stating and explaining that. Okay, and then for parts A and B, you get 1 point for both of them combined if you used correct units. So that would be feet per second squared in part A, and then feet in part B. Okay, question 5. So I think for this question, the AP test creators were like, alright, we know you struggled with that Oregon question and with the periodic question, so we'll take it really easy on you with this question 5. Really, really easy. So we have a differential equation, dy dx is 1 plus y over x, where x is not equal to 0, as you can see here. On the axis provided, we need to first sketch a slope field for this function, okay? At the 8 points indicated, 1, 2, 3, 4, 5, 6, 7, 8. So let's see what we can do. So we know that when y is -1, the derivative is going to be 1 plus -1 over x, which is 0, right? For x is not equal to 0. So whenever y is -1, the slope of the function is 0. So we can sketch when y is -1, which is at these 2 points, the slope is going to be 0. Something like that. Right, slope is 0, okay? And then for the rest of the 6 points, we're just going to have to go one by one and fill it in, right? Here, at x equals 1, y equals 0, the slope is going to be positive 1. So we'll have something like that, maybe. And then here, slope is going to be -1. Here, slope is going to be -1 comma 1, so it's going to be -2. It's going to be very steep. Here it's going to be 1 comma 1, it's going to be +2, very steep. Here at 2 comma 0, it's going to be 1/2, so not very steep. And then here it's going to be -1/2, not very steep again. So this was the slope field, which basically, remember, it's like a sketch of the slopes at a bunch of different points. And this slope field was worth 2 points for doing it correctly. Part B, find the particular solution y equals f of x to the differential equation with the initial condition f of -1 equals 1 and state the domain. Okay, so the first thing to do to solve a differential equation is to bring the x's to one side and the y's to one side. So we'll bring x's to one side, we'll bring the x's to the right and the y's to the left. We'll have 1 over, oops, one sec. Okay, thinner brush now. We'll have 1 over 1 minus y dy equals 1 over x dx. Now that we have the y's over here, x is over here, everything's in its own place, we can integrate both sides. Okay, so the integral of 1 over y is going to be, oh, why is it, it's 1 plus y, right? Was it? It's 1 plus y. I don't know where the minus came from, sorry. So since the coefficient for the y is 1, we can treat this whole thing just like it's a single thing, and we'll call it the natural log of 1 plus y. If this was like 1 plus 2y or something, we would have had to do a u substitution. Okay, so anyways, the natural log of 1 plus y equals, the integral of this is just going to be the natural log of the absolute value of x plus c. Okay, now we need to get y by itself, so we'll have both of these as the base, or these both will be the exponent with a base of e. The reason we're doing that is we can cancel the e's and the natural logs here. So we'll have 1 plus y equals e to the natural log of the absolute value of x plus c. Okay, since we're adding two things up in the exponent, we can split that up into e to the natural log of the absolute value of x and e to the c. Now we'll do two things here. First, the e and the natural log will cancel out again, leaving us just with the absolute value of x. And then we have e to the c. This is just a constant number, right? So even though this c and e to the c are not the same value, we can just say 1 plus y equals the absolute value of x times c. C is just a constant. Remember, it's not a particular number, it's just a constant. So we have this, and then we can solve this for y, like that. And then now's the time where we apply the initial condition. Remember, negative 1 comma 1. F of negative 1 equals 1. So we can plug that in here. We'll get 1 equals absolute value negative 1 times c minus 1. Absolute value of negative 1 is 1. So we can add 1 to both sides and get c equals 2. Okay, so if we plug that back into c here, we'll get y is 2 times the absolute value of x minus 1. And that's the differential equation solved. But we also need to find the particular domain. Okay, so because of the absolute value, we have two options for the domain. X is greater than 0 or x is less than 0. And since in the initial condition they gave us, f of negative 1 equals 1, we know that x is less than 0, right? F of negative 1. So we're going to be going with this bottom domain here, x is less than 0. So here's our function, and for the domain is x is less than 0, like that. Okay, so this was, hang on, let me count the points. 1, 2, 3, 4, 5, 6, 7 points for this one part. That's insane. So 1 point for correctly performing the anti-differentiation, 2 points, 1 point for separating the variables, 2 points for performing the anti-differentiation, 1 point for including a plus c, 1 point for including the initial condition, 1 point for solving for the constant c, 1 point for correctly finding the differential equation, and another point for correctly finding the domain. Wow, talk about easy points, huh? So that was the end of question 5. Yeah, it was just a two-parter. Let's move on to the final question, which thankfully also was not that difficult. Finally, question 6. The twice differentiable function f is defined for all real numbers and satisfies the following conditions. F of 0 equals 2, f prime of 0 is negative 4, and f double prime of 0 is 3. This really feels like the setup for a Taylor polynomial question, but obviously this is AB, so I'm not going to have that here. So looking at the question, the function g is given by g of x is e to the ax plus f of x for all real numbers, where a is a constant. Find g prime of 0 and g double prime of 0 in terms of a. Show your work. Okay, so to find g prime of 0 first, they want us to take the derivative of this g function. So g prime of x. Well, we'll find g prime of x first and then look at 0. Okay, so the derivative of this function. The derivative of e to the ax, where a is a constant, is going to be a times e to the ax. This is why the derivative of e to the x is e to the x. It's the special case of this where a is equal to 1. Okay, and then we're adding the derivative of f of x is f prime of x. So if we want to find g prime of 0, that's going to be a times e to the a times 0 is 0, plus f prime of x. F prime of 0 is -4, so plus -4. E to the 0 is just 1, and so this just simplifies to a minus 4. Okay, let's just rewrite that to look nice. G prime of 0 equals a minus 4. Wonderful. So now let's look at G double prime, right? Let's do purple. Sure. G double prime of x. So we'll take the derivative of this. If we follow the same thing we did before, a is a constant, e to the ax. The derivative of this is going to be a times e to the ax. But there's already an a there, so we have to make it an a squared times e to the ax, right? So basically a e to the ax times a. And then we're adding the derivative of f prime of x, which is f double prime of x. Okay, so if we want to find g double prime of 0, that's a squared times e to the 0 plus f double prime of 0. F double prime of 0 is 3, so this becomes a squared times 1 plus 3. So g double prime of 0 equals a squared plus 3. Like that. This was 4 points. 1 point for finding g prime of x, 1 point for finding g prime of 0, 1 point for finding g double prime of x, 1 point for finding g double prime of 0. Part B, the function h is given by h of x is equal to cosine kx times f of x, where k is a constant. Find h prime of x and write an equation for the line tangent to the graph of h at x equals 0. So first let's find h prime of x, okay? H prime of x is going to be, so we're differentiating a product, so we're going to have to use the product rule. So we'll have the first thing, which is cosine of kx, times the derivative of the second thing, which is f prime of x, plus the derivative of the first thing, which is the derivative of cosine of kx, which, remember, the derivative of cosine is negative sine. So we'll have negative sine kx. And then since this is a compound function, since there's a k there, we have to use the chain rule and multiply by the derivative of the inside function. The derivative of kx is just k. And then, of course, after that, we have to also keep the f of x there, because this is the first thing times the derivative of the second, and then the derivative of the first thing times the second. Okay, so this is h prime of x. So if we want to find h prime of 0, we'll just plug in 0 into here. We're going to get cosine of 0 times f prime of 0 minus sine of 0 times k times f of 0. And then notice that sine of 0 is just 0, so this entire part of the equation is just gone. And then also notice that cosine of 0 is 1, so we can kind of ignore that as well. So we just have h prime of 0 equals f prime of 0, okay? So if f prime of 0 is -4, like I said, so h prime of 0 equals -4. They also wanted us to write the equation for the line tangent to the graph of h at x equals 0. So the way we're going to do that, since they want us to write a tangent line, immediately you write down two things on your paper. Write down point, write down slope. We need to find a point, so we need to find a point where x equals 0. That's going to be 0, comma h of 0, right? That's the point. And the slope is going to be the slope of the function h at 0, which is h prime of 0, which is -4. So all we have to do now is find h of 0, right? H of 0, since we have a function for h of x, we can simply find h of 0. I'll do it in bright blue. H of 0 is cosine of 0 times f of 0, which is, remember, cosine of 0 is 1, so we're just left with f of 0. F of 0 is 2, right? So h of 0 is 2. Go down here, say that this is 0, 2. Okay, so now that we have the point, we have the slope, we can write our tangent line being y minus y1, so y minus this y coordinate, equals the slope times x minus the x coordinate, 0. That is the tangent line. That is the end of the question, the end of the whole test. And this was a 5-point question. 1 point for correctly finding h prime of x here. 2 points for that. Did I say 1? I don't know if I said 1, but I meant 2 if I said 1. 1 point for finding h prime of 0. That's -4. 1 point for finding h of 0 is +2. And then 1 point for the final correct answer. Okay, that was the end of the 2006 test. I hope you found this helpful, and I will see you in the next one. Goodbye.